Hello and welcome to our next lecture. This is part 2 of our measurements. You've already hopefully watched part 1 of this lecture. So if so, let's get right to it. Professor, take it over. Okay, welcome back here. This is continuation here of chapter 2 we are in. Last time we talked about measurements. We talked about how to take measurements. We talked about different units, the English system, the metric system. We talked about prefixes. We're going to talk about that in just a second here again. We talked about significant figures, how to count them, how to do calculations with them. So again, this will be a second part here, I think, to our chapter 2 lecture and a continuation from the previous one. So let's finish up, hopefully, the rest of chapter 2 here. So we're going to continue on talking about prefixes and how to use these prefixes. So we touched upon them as we went through mass, we went through volume, and again, using those different sort of prefixes to change the meaning of them. This, I would say, is a very common sort of table and how you will get these guys in terms of what they mean. So again, here we have something like centi is 10 to the minus 2. So when you see something where it says centi is 10 to the minus 2, by the way, that is scientific notation. And if you do need to put it in your calculator, depending on the type of calculator you have, probably any type of calculator really, you can just think of it as basically 1 times 10 to the minus 2. Remember, obviously, you would want to use your exponent button that we talked about when you would be doing those type of things. But as I mentioned earlier when we went through some of these examples, it is a very common error that people make when they go to sort of do these conversions. They always want to do them backwards. So once again, when you see this power of 10 equivalent, that is how much there is in the base unit to one of the prefix unit. So again, if I had 1 centimeter, that is our prefix unit. That would be equal to 10 to the minus 2 meters, which is our base unit. Again, meters in both of them is really our unit. And 1 centimeter would equal basically 1 times 10 to the minus 2 if you need to put that into your calculator. Once again, it is super common error. People always want to reverse those guys and do it incorrectly. So I'll put an X there. Don't do that. Once again, as we talked about, it really doesn't matter what the base unit is. You could still do the same sort of conversion. If we were talking about volume, maybe I have 1 centiliter. That would be 10 to the minus 2 meters. Not meters, liters. There would be a much better unit. Let me get my eraser out here and clean up that thing. It's a good thing they invented erasers. Try that again. Base unit here is liters, so that would be 10 to the minus 2 liters. If I had 1 centigram, that would be 10 to the minus 2 grams. So again, it doesn't really matter the base unit. Centi is sort of the prefix unit, and it all works the same. Again, you can pick any one here. Nano is a very common one that we come across a lot of times in chemistry, especially later on. As you go to first semester general chemistry, you'll come across nano a lot. Once again, if you have something like 1 nanometer, that would be 10 to the minus 9 meters. So if you had 1 nanogram, that would be 10 to the minus 9 grams. So it's very important to make sure you understand how to use this. Some people will use perhaps kind of the larger numbers, if you will, the non-scientific notation, which is over here. And again, you could get that, sometimes by just kind of dividing things out. But either way that you use it, you want to make sure that you also use it correctly. And a lot of errors in this type of situation. For example, here, micro, which is this symbol right there. And micro is 10 to the minus 6. So if I have 1 microgram, that would be 10 to the minus 6 grams. Once again, that essentially, if you need to put it into your calculator, is 1 times 10 to the minus 6. And again, as we would put that in, 1 exponent button, negative button, and 6. Now, depending on your calculator, and I don't want to say for everybody because it is really calculator dependent. Sometimes you do need to put this into your calculator like that. Some calculators, for example, like the one I have right here, and some other ones, you actually could, in a lot of cases, just do the exponent part and just do the to the negative 6. But to be on the safe side, since I don't know what everybody's using in terms of calculators, and everybody could be different, probably just put it in as 1 times 10 to the minus 6 and you'll be good. So keep that in mind. What we see over here is how much there is in the base unit to one of the prefix units. And again, super important that you understand how to do that. Continuing on, talking a little bit more about length. These are, I would say, some of the popular are very common sort of length equalities. A reminder that an equality is two values that represent the same amount of a substance, but are on different units. So, as we'll talk about a little bit here in just a second, something like there are 100 pennies in $1. So that is, they both represent the same amount of money, but they are on different units. And that's what an equality basically is. So these are very common ones that I think, touched upon earlier in the previous lecture. 1 meter is 100 centimeters. 1 meter is 1,000 millimeters. And I think when we're looking at the ruler there, 1 centimeter is 10 millimeters. So those are very common sort of conversions that we deal a lot with. Measuring volume, some very common equalities. Again, I would say these two guys here, or this one here, is probably the most common sort of volume conversion that we use a lot, or volume equality that we use a lot, and that is 1 liter is 1,000 milliliters. By the way, these are some different equipment that we can use to either measure out volume or transfer volume. This is a graduated cylinder, which again, if you look at some of my earlier drawings, looks just like that. If you kind of close your eyes from my earlier drawings, maybe it'll look very similar. But here, that is a graduated cylinder. It's a very good piece of equipment to measure out a certain volume of a liquid with very high accuracy and probably precision. This is what is referred to as a volumetric flask. Volumetric pretty much means expensive, so you should never break these things. It also usually means that they have one marking, and on this one is right here. I'll just make it really big. It has really one marking, and when you fill this volumetric flask up to the marking, you will have the volume that it is. Typically speaking, when we go to record something that's volumetric, usually that is 2 decimal places is how we record it. So something like this would usually be recorded as 100.00 milliliters when it's dealing with volumetric. This is a burette, which is a equipment that's used actually to deliver a very specific amount of volume. This is used in a lot of experiments known as titrations. And burettes are actually a little bit different, as we can perhaps maybe make out up here. We actually filled the burette up on the top, and it actually will obviously deliver the volume out the bottom here. And kind of different in terms of the scaling is if you fill it up to the top, that's 0 milliliters. And at the bottom, it actually gets larger. So for example, when we go to read something like a burette, this would be 0, this would be 1, this would be 2, and so forth. So it actually increases volume as you go down. So sometimes people make a incorrect reading when they have that. So let's just say we had our liquid right about there. It's between actually the 1 marking and the 2 marking. And since it actually increases as you go down, this would be like 1.50 milliliters and not 2 point something. So again, we fill from the top here, X is from the bottom. So it actually increases as you go down. Another very common mistake that people make is they'll fill it to the very top. However big the burette is, say 50 milliliters, they'll fill it to the top and put 50, and you will get the wrong reading. So it's very important to understand the scaling and the measuring markings that we see. And in the case of like a burette, it actually does increase as you go down. This is a pipette. This is actually a volumetric pipette, and it also has 1 marking. You know it's volumetric because it kind of comes out here. And that's pretty typical of a volumetric pipette. A graduated pipette, which is sometimes used, that doesn't really have kind of like the bubble in the middle like this one does. And a graduated pipette has a lot more markings on it. This has just 1, so very similar to our volumetric flask here. You fill it to the line, and again, I exaggerated the line obviously right about there. And that will give you your volume. And in this case, if this was say 10 milliliters, can't really see the number there, but I'll go with 10. We would also usually record this to 2 decimal places. This is a syringe, which obviously draws up liquid from the bottom and then obviously dispenses it coming back out. So these are some very different sort of pieces of glassware. Each are used for different things. Some are used very well for measuring volumes. Some are used very well to accurately sort of transfer a certain amount of volume. There's good pieces of equipment to do volume measurements and bad pieces of equipment. For example, if you took just a beaker, and if you look at like a 50 ml beaker, you may see 40 marking, 30, 20, you'll see some markings. And if you actually measure out trying to use a beaker to measure a certain volume of liquid, it's actually a really terrible piece of equipment to use to try to measure out a very accurate amount of a volume. The meniscus is so spread out, you really can't get an accurate reading. There's usually not a lot of markings, which means you would be very surprised. So for example, if you did fill this up right about where we had it, and you may go, oh, I got about 35 milliliters, you might actually find yourself well below that, even though it may appear to be 35. So it's not a greatest piece of equipment. That's why graduated cylinders are much better pieces of equipment to measure out a volume. Now, we talked about this earlier. This 3-pack of conversions are really important. This is, again, a volume. And then we got that by taking the length times the width times the height. And again, as we talked about earlier, if they were each measured in centimeters, we multiply those together, we get a cubic centimeter, which once again is a volume. Each of these individual guys, as we talked about earlier, are length measurements. But if you multiply 3 length measurements together, especially for a cube, that will give you a cubic centimeter in this particular example, and that is a volume. 1 cubic centimeter is the same as 1 cc, and that is usually what is used in sort of medicine, like the syringe we just saw. When you hear that maybe a medical shows give the guy 5 cc's of this or something like that, they're talking about cubic centimeters, which is basically a milliliters here. So 1 cubic centimeter, which is normally how we would probably see a cubic centimeter, again is equal to 1 milliliter. And that is also a conversion that is used a lot here in chemistry. So here again is a graduated cylinder. And when we see 1 centimeter by itself, we're talking about a length, but again, a cc or a cubic centimeter is that. By the way, if we take a look at the scaling, which is a graduated cylinder, has a slightly different scale than some of the ones we just saw. We look at our big markings here. That is 60. That is 70. And that means that our large markings here represents 10 milliliters. Once again, here we would count. So that is 1 marking, 2 markings, 3 markings, 4 markings, and 5 markings. So each of our smaller markings is basically 10 milliliters divided by 5 is 2 milliliters. So again, this would be like 62, 64, 66, 68, and 70 going up that. Now, how far can we take this? Once again, we normally could go one more place to the right of the smallest marking like we talked about. We also can very quickly figure that out by taking the smallest marking value and dividing it by 2, which is 1 milliliter. And that is what we talked about, kind of our plus or minus 1 milliliter in this case. That means that we could actually take it to a whole number. So again, if we were kind of in between these markings here, that first marking is 62. The second marking is 64. We're in between. We're going 63 milliliters. That would again have 2 significant figures where our uncertain number is going to be the 3 in this case. We'll throw back reminder what we talked about in the previous lecture there, how to properly take a measurement. Measuring mass, as we talked about, these are very common inequalities. I would say out of these two here, or 3, the first 2 are definitely the ones that we see the most. 1 kilogram is 1,000 grams. 1 gram is 1,000 milligrams. In terms of mass, kilograms, grams, and milligrams are super common sort of units that we see a lot in chemistry. One way that we do measure mass, and as we talked about, there is a difference between mass and weight. Remember that weight does take into account the force of gravity, while mass is independent of that. We use a balance, and these are 2 different forms of balances. Balances are basically a fancy word for scales, basically. And these are digital ones. This is what's sometimes referred to as an analytical balance. It usually has kind of an enclosure here, and also usually will go to more decimal places when it gives you your reading. This one doesn't actually have a top to it, but works the same way. We do, when we take anything that is digital, as we talked about, all of the numbers are important to record. They're all significant. So again, here we would not just want to record the first couple numbers. All of them given to us is really important, and we want to do that. By the way, when we use something like a balance, there's usually a button that's like a tare button or a 0 button on it. And if we go to weigh something using a balance, typically we 0 out the balance first, make sure that it's kind of all zeros up there on the display. We would open the door if it had a door, put whatever we want to measure the mass on in there, shut the door, wait for the numbers to stop. Same approach here, just not the opening the door part. You would 0 it out, put it on there, and you would weigh it. All right, so a plastic IV bag contains 1,000 milliliters. So in 1 liter, there's 1,000 milliliters. So we would have 1 liter is a 1,000 milliliters. Not quite sure what the question was there. I feel like it's missing, but I'm gonna go on from that one. Here we want to complete these again. For some of these that we saw, 1 kilogram is 1,000 grams, and 1 milliliter is, as we see there, 0.001 liters, or again, 1,000 milliliters is equal to 1 liter, which is what you get if you divide this to both sides. All right, so let's then talk about conversion factors and writing conversion factors and sort of what it is. We're going to kind of be talking now about conversion factors and dimensional analysis and problem solving. So writing conversion factors, a conversion factor is really written from an equality. And from any equality, you basically write two conversion factors, which are essentially just fractions. So for example, if we have 12 inches is equal to 1 foot, we could write two conversion factors for that. We could say that there are 12 inches over 1 foot, or 1 foot on top is 12 inches. So these are equalities here. That's the equality. And these are the conversion factors that we could get from that one equality. How do we use conversion factors? Well, we really use them in the sense of doing problem solving. And it's through a way that we do it, which is, as we'll talk about here in a few slides, and we'll talk a little bit about it now, is what is known as dimensional analysis. And dimensional analysis is setting up problems where we use conversion factors, and it's kind of a unit cancellation sort of situation. We want to cancel out the units we don't want, and we want to keep the units that we do want. And it goes down to a basic idea of opposite cancel. So whatever unit you want to get rid of, you need to put it in the opposite location. So what do I mean by that? Let's just take a straightforward example. Maybe let's say we had 45 inches and we wanted to know how many feet that would be. So the first thing that we would want to do is really start with what was given to us, which is 45 inches. And although it is not written as a fraction, it essentially is 45 inches over 1. So why is that important? That's important because the units of inches are basically up on top. And we do want to get rid of it, which means to get rid of it, we want to put the units of inches in the opposite location. Looking at our two conversion factors here, the one where we see inches in the opposite location is this one right here on the right. And that is what we would want to use. So we would do a little parentheses. We would set in our fraction here, putting the inches on the bottom in the opposite location. And up on top is 1 foot. Now, what we're going to do now is essentially multiply whatever is on top. So whatever is on top is going to get multiplied. And then we're going to come back and divide by basically whatever is on the bottom. So if we do that for the numbers here, we will take basically 45 times 1. You don't necessarily have to do that. We would then divide it by 12. And on our calculator here, it will give us 3.75. So let's talk about what happens with the units here. We are going to cancel out the units of inches because inches are on top. And we also have inches on the bottom. They essentially cancel each other out and become 1. And to see it with kind of a number sort of situation, if we took 2 divided by 2, that would equal 1. So units work the same way. If you kind of have the same unit on top and the same unit on the bottom, they will cancel each other out and become 1. And that's what happens here. That leaves us really just this unit that is left, which would be feet. Now, the other thing that we need to look at when we do a problem like this is significant figures. So in this case, we are basically multiplying and we are dividing. And remember that when we multiply and divide, we look at the number of significant figures. So when we look at this number, it has 2 significant figures. If you remember our conversation, this is considered an exact number, which means that it has as many significant figures as you would like. And one of the things that we look at when we do calculations like this is because it's considered an exact number, we don't have to worry about it in terms of our answer. So really the only thing that's going to determine how many significant figures our answer should have is actually going to be that first number, which is 45, and that's 2 significant figures. That means technically we should end our answer right here at the 7. We have to look at the 5, which means we then should round up. And our correct answer here should be 3.8 feet, which would be 2 significant figures. So we use these conversion factors in these problem solving and dimensional analysis sort of ways to get rid of units. And that's the whole idea of dimensional analysis, is basically the units we don't want, we get rid of, and we want to be left with whatever units we're looking for. So hopefully that kind of makes sense. We're going to see some more examples here as we continue on. So let's talk a little bit more about this. Again, this is basically sort of what we were just talking about, just using the 100 pennies and $1. Again, a reminder that it does represent the same amount of money. You have 100 pennies equals $1. If you go through the drive-through, you can pay in pennies, you can pay in dollars. Maybe if you pay in pennies, they might put your picture up there and not take your order next time, but technically it's still money and you could pay either way. It represents the same amount. And obviously here we could write 2 conversion factors of 100 pennies over $1. Or the other conversion factor would be $1 over 100 pennies. Here are some common equalities, and what we see here is really the 2 types of units that we've been talking about. We have the US or English set of units, and we also have the metric or SI set of units, and then we have crossover units. So let's talk a little bit about each of these. I would definitely say some of these here we come across a lot, like 12 inches of the foot, 5,280 feet in a mile, 4 quarts in a gallon. Metric, definitely pretty much everything on the metric side here comes across a lot in these things. Time, hopefully this is some of the stuff that you should know, may not be provided for you. So a reminder that there are 60 seconds in 1 minute. There are 60 minutes in 1 hour. And the place where sometimes people mess up on, there's only 24 hours in 1 day. Sometimes people go 60 seconds in a minute, 60 minutes in an hour, like 60 hours in a day, too many hours. So don't mess that up, which is again a common mistake. Now here we have some crossover. This is actually an exact conversion. 1 inch is 2.54 centimeters. This is 0.621 miles is 1 kilometer. So I would say that pops up a lot. Quarts and milliliters as well, pounds and kilograms, and 1 pound is 454 grams. The full number there is 453.6 grams is 1 pound, but that again is metric to English. So these are some common equalities that you should be familiar with. What do we do with these equalities in terms of calculations? So what I mean by that is a couple of things. For any of these guys here, we could write 2 conversion factors and use them in calculations. Now, when we talk about exact numbers, and as we just saw in that sort of example we just did, when we have something that's considered an exact number, you don't have to worry about it in terms of your answer. So if you are using really an US or English to English conversion, they're considered exact numbers, which means you don't have to worry about it. If you are using a metric to metric sort of conversion, like some of these clear are not all the English conversions or metric conversions there are, but these are just some of them. That's considered an exact number. So you don't have to worry about it in terms of your calculation. The one place where technically speaking, you should worry about the significant figures if you use an equality is if you cross over between English and metric or US and metric. You usually do have to look at that conversion factor in terms of their significant figures. One exception that you don't need to do is this one, which is still considered an exact number. So for example, if you are going to use a conversion where you would technically want to look at that crossover. So for example, if we grab this guy here, we could write two conversion factors, 1 kilogram over 2.20 pounds, or 2.20 pounds is 1 kilogram. So when we would use this, say, in a calculation, you typically will always have, when you kind of do metric to English conversions, is you'll usually have one of the parts as a 1, and that clearly is not what you're looking at. So we would actually count this as 3 significant figures based off of the 2.20 pounds. So if we did, say, 52 kilograms, and we want to know how many pounds that would be, we have kilograms up on top. We would want to use this as a conversion factor. 2.20 pounds is 1 kilogram. Kilograms would cancel. Once again, we're going to multiply what's on top. We're going to divide by what's on the bottom there. And we would take 52 times 2.2. That's going to give us, there we go, 114.4 pounds on our calculator. So what should we do with significant figures here? Well, in this particular case, we should look at the significant figures of our first number, which would be 2 significant figures. Here, because it's a crossover sort of conversion, we should look at it, and that would actually have 3 significant figures. So we're still going to go with 2 here since we're multiplying, and that's going to take us really to 110 pounds as our correct answer in this case. I would say not 100% of the time, but fairly close to it. In most cases, you probably would be correct or not too far off if you kind of look at the original number and all you're doing is a conversion type of problem. If that original number of significant figures is usually about the right number of significant figures you should have on your answer. I won't say 100% of the time, but I'll go 92% of the time, probably that original number is going to be pretty close to the right number of significant figures. I would say in a lot of cases, even if you do have to look at the significant figures of a conversion factor, a lot of times still that first number that you're converting has the least number of significant figures. But again, not always the case, and you should look at it. So English to English conversion factor, not a problem. Just ignore it in terms of the answer and its significant figures. Metric to metric, ignore it in terms of the answer, in terms of how many significant figures you should have. Metric to English, you should take a look at it and evaluate it in your calculation. The other place where you should really look at things that you use as conversion factors are conversion factors that sort of come from the problem itself. So they're kind of specific to just the problem. They're not always the case. Like, for example, if you were walking at a certain rate or driving at a certain rate, like 25 miles per hour, you probably should look at that in terms of its significant figures, because it's not always 25 miles an hour. That's specific for the question. So sometimes you'll actually be given some conversion factors within a problem, and you should look at those as well in terms of their significant figures. So let's take a look here. If we have this equality and we want to write the 2 conversion factors that go with it, why don't you take a second and write them? Okay, so the 2 you should have came up with is we could put 5,280 feet up on top over 1 mile. The other conversion factor, 1 mile, is 5,280 feet. Once again, in a problem, you would not use both of these. You would use whichever one that you needed. So if I was traveling 425 miles, and I want to know how many feet that was, I would again start with my 425 miles. Once again, not written as a fraction, but basically miles are up on top. So remember, opposites cancel. So we're going to look for this guy, and we will go with 1 mile on the bottom is 5,280 feet up on top. The miles will cancel. We're going to once again multiply what's on top and divide what's on the bottom. In the next case, there's only 1 on the bottom, so not much to divide by. So 425 times 5,280 going to give us a number here of 2244,000. And in this case here, I think I got it all right there. 2244,000. There we go. We would look back here. 3 significant figures would take us to here. And that means it would be 2240,000. We would want units of feet here. Or we could again use our scientific notation. 1, 2, 3, 4, 5, and 6 gives us 2.24 times 10 to the 6 feet. Once again, 3 significant figures really based off of our first number over here. If we were driving a car 65 miles per hour, so whenever we have 2 sets of units, miles per hour, the per basically means fraction. So miles over hour. So this basically means that we would have 65 miles over 1 hour, or in 1 hour, we basically can travel 65 miles in that particular time period. When we do have, for example, something like this, say 65 miles per hour. And let's just say, for example, we wanted to know how many feet per minute that would be. Now, in this particular case, we are looking at converting not 1 unit, but actually 2 units. We need to take miles to feet and hours to minutes. So in this particular case, we could look for some equalities that would help us do that. We could use the one we just saw. 5,280 feet is 1 mile. We could also use our time, which I think we also talked about. I'm going to try to do this right without messing it up. 60 minutes, again, is 1 hour. So these are 2 equalities that we could use to help us do this conversion. Remember that from each of these, we could write 2 conversion factors, 5,280 feet over 1 mile. Our 1 mile is 5,280 feet. For our second one, we could do 60 minutes over 1 hour, or 1 hour over 60 minutes. So when we do this type of conversion here, if we were going to do it, we would start with what was given to us. And really, you could just think of it as 2 separate conversion factors, but I would just set it up here dimensional analysis way with our fraction so we could clearly see where units are. So the first thing I'm going to do is get rid of the miles. And because of the way I set it up, I could clearly see miles are on top. So opposites cancel, which means I'm going to use this one, which has the miles on the bottom. That's 5,280 feet is 1 mile. If I were to stop right here, the units of miles would actually cancel out. And what I would be left with in terms of units at this point is feet up on top and hours on the bottom. So by just doing that conversion, I have successfully converted the top part of it, of what I need. I still need to convert the bottom. And this is why it's really important to set it up like this. I can now clearly see that my hours are on the bottom, which means to get rid of them, I need to go opposite and put my hours up on top, which would be this guy. So I can actually get an answer here, or I could just continue on with the calculation. That's what I'm going to do. Again, we want to put the hours up on top, the 60 minutes on the bottom. Hours on top, hours on bottom are going to cancel. Now I am left with, at this point, feed still up on top and minutes on the bottom. I have now successfully converted it to the units I need. All that's left to do now is the math part of it. So let's talk a little bit about the math part. Once again, here we're going to multiply by whatever is up on top. Then we're going to come back and divide by whatever is on the bottom. So when you do this type of conversions, and definitely when you do these sort of problem solving and setting it up this way, which is what they expect you to do as you go through your chemistry classes, is to set up these things showing dimensional analysis. It's really important, once again, as we talked about earlier, the calculator, and how to punch it in correctly. Sometimes, a lot of times, people will have the problem set up correctly, but when they go to punch into their calculator, they try to punch everything in at once. And that's fine if you know what you're doing and you put parentheses around things that need parentheses. But if you just sort of put things into your calculator all at once without the right parentheses, you will find yourself sometimes with the wrong answer, which is not what you want to do. So my recommendation is, on the top here, when you have something set up like this, you can multiply as many numbers as you like. So here, for example, I would take 65, I would multiply it by 5,280. I can multiply by 1. I don't really need to, but I could. Then once you get done multiplying everything you have up on top, you should hit equals. And in this particular case, I actually really only have one number on the bottom that you need to divide by. But if I had multiple numbers, for example, I'll punch the numbers in here. I would hit the divide button and divide by 1, which in most cases you don't really need to do. Then you should hit equals. Then I would divide by the next number, which is 60, and then hit equals. And if you kind of do that step by step, dividing the bottom here by each number individually and hitting equals after you divide by each number, you will get the right answer pretty much every time. If you try to punch all that in at once, it's a 50-50 shot. You might not get the right answer. So just keep that in mind as you're punching things in your calculator. You want to make sure you don't put too much in at once, and use that equal sign a lot as you do it. This gives me, by the way, something like 5,720. My units here are feet, which is where the number should stay with, per minutes on the bottom, basically 1 minute. We always give an answer like this where if you do have 2 units, you never give a fraction. So you would never give something like, here we go, 65, 5,280. You never give something like 343,200 over 60. You would want to divide it out. So you should always give it like that. In terms of significant figures here, if we look at what we got going on, that's an exact number. You don't really have to worry about it. Don't really have to worry about it there either. So it really is this first number that we do have to worry about, which is actually 2, which means we do actually have to clean this up to 2 significant figures, which is there. And once again, probably should end up with 5,700 feet per minute. So sometimes you may have multiple units that you use as a conversion factor like we did here. And even in a problem like we just did here, you might have multiple units that you need to convert. So by setting up like this, again, with dimensional analysis, you could clearly see where the units are, and you could clearly see that you just need to go opposites. You can clearly see it's on top and what's on the bottom. I would say it's a very common mistake that sometimes people, when they don't write it in dimensional analysis, and they kind of lose track of what they should be doing. Should they be multiplying? Should they be dividing? Something like this, it would be a very common mistake. Somebody would probably put the 60 minutes up on top and the hour on the bottom and actually multiply by the 60 instead of divide. So by keeping the units separated like this, it makes it very, very easy to do the math, hopefully correctly. A couple other examples of some conversion factors. If we filled up gas and I went for 91 octane at 305, wow, that's a pretty old slide, I suppose. I would love 305 gas right about now, but by the way, that was pretty expensive when I wrote it, I think. We could turn that into 1 gallon is $3.05, or for $3.05, we could get 1 gallon. Again, our two conversion factors. Also, in chemistry, sometimes we're given percentages, and we have to kind of sometimes turn them into usable conversion factors. And one way that if you have a percentage and you want to kind of turn it into a usable sort of conversion factor, assuming 100 of something is a good way of doing that. Like if you got 80% on your exam, you probably got 80 points out of 100, right? So it keeps the numbers the same. So if we have somebody that has 12% body fat by mass, that would mean, for example, you would have 12 kilograms over 100 kilograms of body mass, or 100 kilograms of body mass is 12 kilograms of body fat. Or you could use more of an English conversion like pounds, 12 pounds of body fat over 100 pounds of body mass, or 100 pounds of body mass over 12 pounds of body fat. If I had a 2% by mass solution of, say, sodium chloride, that's mass to mass, M over M. That's what the M over M means, mass to mass. That would be, for example, I would have 2 grams of sodium chloride and 100 grams of solution, or in 100 grams of solution, I would have 2 grams of sodium chloride. So again, assuming 100 is nice because when you can turn a percentage basically into the same number, the number doesn't change. It stays the same basically as the percentage. So we've kind of talked about this together here with kind of writing conversion factors, but dimensional analysis is really the approach that you should take when you're setting up problems in chemistry. And again, it really is where we use a conversion factor from an equality like unit A is equal to unit B. And, you know, if we start with 1 unit that we do not want, we can use that equality and a conversion factor to get rid of the unit we are not looking to keep and end up with the unit we are looking to keep. So that's the idea behind dimensional analysis. If you are solving for something 1 unit by itself, that unit should really end up on top. If you're solving for 2 units, you may have a unit on top and a unit on the bottom, kind of like what we just did there with the, was it feet per minute, I think is what we ended up with. There are several steps that you could follow when you're doing these type of problems, and let's talk about them. You should write what's given to you in the problem, and that goes for a lot of chemistry problems. If you kind of write what's given to you in the problem, oftentimes it will kind of lead you down the right path of how to solve it. If it's some type of equation, you can kind of figure out maybe what equation would make sense to use. Maybe find what you are looking for. You want to think about what equalities will get you there. Now, there are different pathways when you're doing conversion factors, especially. So there are different ways to get to the same answer. And there's not necessarily a right way or a wrong way. As long as the pathway you choose to get to that answer, you're using legitimate conversions and not ones you make up yourself. You think about the appropriate conversion factors that you would use. You would set up the problem where you can see the units canceling and obviously solve the problem to the correct number of significant figures. All right, so let's take a look at one here. It's a pretty straightforward, simple one. How many pennies are in $3? Once again, our goal here is to start with pennies. Dollars. Actually, it's the opposite way around. So let me just erase that and give that a go again. Here we are starting with dollars. We ending in pennies there. That looks a little bit more correct. Here we want to think about the equality. So like our 100 pennies is equal to $1. That's going to give us two conversion factors. Once again, 100 pennies over $1. Or we could have $1 over 100 pennies. So starting with what was given to us, which is $3. Once again, dollars are up on top. So opposites to cancel means we are going to use this conversion factor here. Up on top would go our 100 pennies. On the bottom would go $1. Dollars will cancel, and that would get us something like 300 pennies here. Again, multiplying across here. Coming back and dividing, not really necessary in this case since it's only 1 on the bottom. This is an exact number, which means really this is the only guy that we have left, and we can look at it as one significant figure here. All right, let's take a look at another one here. So why don't you give this a go and see what you come up with. I'm going to give you some equalities that might be helpful. You go to the local AM/PM to the Thirst Oasis there, and you get yourself 32 fluid ounces of Diet Coke. We're looking for how many gallons of Diet Coke did you drink? So take a couple minutes here, set it up using dimensional analysis, use your conversion factors, and see what you come up with. Okay, so let's see how you're doing. We're obviously starting with fluid ounces. We want to eventually end up to gallons. So we could go from fluid ounces to quarts and quarts to gallons. So sort of our first and second step here. These are two equalities that will get us there. For our equality over here, we could write 4 quarts is 1 gallon. Our 1 gallon is 4 quarts. For our equality over here, we can have two conversion factors of 1 quart is 32 fluid ounces. Our 32 fluid ounces is 1 quart. So starting with what was given to us, which is 32 fluid ounces. Once again, our fluid ounces are up on top. So we want to go opposites to get rid of it. So that is the conversion factor there on the left. It's going to do that. We're going to go with 32 fluid ounces is 1 quart. If I stop the calculation right at this point, fluid ounces on top and bottom would cancel. I am left right now in units of quarts, which is close to what I'm looking for. But I then need to go from quarts to gallons. So that's going to be my next step. So because I set it up here with dimensional analysis, I can see quarts are up on top. That means, again, opposites to cancel. We're going to take the guy on the right there. 1 gallon up on top is 4 quarts. Quart on top, quart on the bottom will cancel. We're going to multiply once again everything on the top. We're going to come back and divide by what is on the bottom. Once again here, I'm going to multiply at what I got on top, which is basically 32 times 1. I'm going to hit equals. I'm going to divide it by the first number on the bottom, which is 32. I'm going to hit equals. I'm going to divide it by the second number on the bottom, which is 4. I'm going to hit equals. That will give me an answer of 0.25 gallons as the only unit that's left standing, which is what we're looking for. Sort of an exact number, 2 significant figures. Answer here has 2 significant figures in this particular case. That is the correct answer. By the way, 1/4, not the correct answer. That makes me think you're too lazy to divide it. So you should never, ever again give an answer in as a fraction. You should divide it out and get a number. Not necessarily super bad in that situation, but I have had people write things like 455 miles over 3,233 hours and box it. Don't do that. So never give an answer as a fraction. Divide it out. And if you do have 2 units, you should end up with just one number. Or if you have 1 unit like we do here, you should end up with 1 number. So never give an answer as a fraction. Divide it out, get a number. All right, let's take a look at another one here. During surgery, a patient receives 5 pints of plasma. How many milliliters of plasma were given? We have 1 quart is equal to 2 pints. And why don't you give that a go and see what you come up with here. Another conversion that might be helpful for you, 946 milliliters, as we saw earlier, is equal to 1 quart. So that's another quality that might be helpful. So why don't you give it a try, see what you come up with. Okay, so let's take a look. So again, sort of your pathway here. We're starting with pints. Take pints, the quarts, using that first equality, and take it the rest of the way there with our milliliter sort of conversion happening there. So here we'll start with our 5 pints. Once again, our pints are up on top, so we want to go opposite. So if we think about our quarts to pints conversion here, we have 1 quart over 2 pints. Are 2 pints over 1 quart. So opposite to cancel means we're going to use it in this fashion. That's going to put 1 quart up on top, 2 pints on the bottom. We stop the calculation right at this point. We are in units of quarts, which once again is halfway there. We need to go the rest of the way. We're going to use our other guy as a conversion factor here. And again, we could go 946 milliliters over 1 quart. Our 1 is 946 milliliters. So now setting this up dimensional analysis, we could clearly see quarts are up on top. So that means we will use the conversion factor here on the left. And we're going to go with 1 quart on the bottom, 946 milliliters up on top. We will get rid of each of these things, our quarts, and that leaves us with milliliters. So we're going to multiply across the top there. That's going to be 5 times 946. We're going to divide it by 2. Going to get us on our calculator 2365 milliliters. So let's talk a little bit about significant figures here. That That is 2 significant figures. That's an exact number, so we don't have to worry about it. This is a crossover sort of conversion, so we should look at it, which actually has 3 significant figures. That means that we should end up with actually 2 here based off of that first number, which is the lowest since we're multiplying and dividing. So we look at the number of significant figures. That means we're looking at like 2,400 milliliters in this case. Or again, you could use scientific notation 2.4 times 10 to 1, 2, and 3 milliliters. So either one of those are okay. So hopefully you can start seeing the pattern here. Opposites cancel. You want to make sure that you set those things up correctly so that everything cancels out. So here you are stranded 125 miles away from home. You decide, heck, seems like a nice day. I have no money anyway, so let's just have a nice little walk. And you walk at an average rate of 55 feet per minute. How many days is it going to take you to get home? A reminder that there are 5,280 feet in 1 mile. All right, so see what you come up with here and take a moment or two to do this one. Okay, so let's see how we're doing. So clearly we're going 125 miles on that nice fun walk. We're moving at a rate of 55 feet per minute. And we want to know basically how many days is that going to be. So days is a unit of time. This is kind of distance or length in time, and this is length. So we could really use that rate as a conversion factor. We could use it the way it's written as 55 feet per minute. We could also flip it around if we needed to, put minutes up on top and 55 feet on the bottom. We do have a little issue here in terms of units. Our length of miles and feet are different units. So we can't use that as a conversion factor the way it's sitting. We either got to convert miles to feet or feet to miles. So I'm personally here going to convert miles to feet to start with. So I'm going to take 125 miles. I'm going to use my equality above there to go opposite. So that means I need to go miles on the bottom and feet up on top. Again, the miles will cancel. And if we get the answer there, that's 125 times 5,280. Going to yield us 660, 000 feet. So now my distance is in feet, which masks really my conversion factor here. So continuing on with the calculation, 660, 000 feet. That's up on top. So once again, to cancel it, we want to go opposite. So we actually do want to kind of flip this conversion factor and use it in this version where minutes go up on top, 55 feet go on the bottom. The feet are going to cancel. If I stop right at this point, I am in units of minutes. And that's good because eventually I want to get to days. So now that I have it in minutes, I could go minutes to hours to days as my pathway. So this again, we could see minutes are on top. So we want to get rid of minutes. And there are again 60 minutes in 1 hour. If I stop right at this moment, minutes will cancel. And the only unit that's left are hours, which are up on top. That's close to where I want to end up with, but I got to go one more sort of step. And we're going to, again, by setting up here with dimensional analysis, we could clearly see hours are up on top. So we want to go hours on the bottom. As we talked about before, that is our 24 hours in one day, not 60, right? So 24 hours will go on the bottom. One day will go up on top. The hours will cancel each other out. So again, here we're going to multiply whatever's up on top and come back here and divide by what we got going on the bottom. So once again, pretty much it's 1 all the way across. So this is again a situation where I have multiple numbers on the bottom. I'm going to again divide by each one individually on my calculator so I do not screw up the calculation. So we'll take our 660,000. We'll divide by our first number, which is 55. I'm going to hit equals. And divided by the second number there, which is 60. I'm going to hit equals. And divided by the last number, which is 24, and hit equals. That's going to yield me a bunch of 8s, and actually 1 8 and a bunch of 3s. So 8.33 days as perhaps our answer. So let's take a look at, is this the correct answer? This is an exact number, not going to worry about it. Exact number, not going to worry about it. Here, this number has 3 significant figures. We do need to look at that because 55 feet per minute is not a exact equality, is specific for this question. So we should look at the significant figures there. This number, if you remember, although I have it written like this, it really originated from this number, which technically was 3 significant figures. So if I wrote in scientific notation or kind of got it to the right number, it should be 3 significant figures. That means basically 3 significant figures here for our answer. Now, a couple of things about when you're doing these separate problems. Here I did it all in one calculation. I did, I think, some of the other ones as well, all in one calculation. You don't necessarily have to do that. You could do the first conversion, like the 660,000 divided by 55 and get an answer. You could then take that answer and do the next conversion divided by 60, get an answer, do the last one divided by 24. Once again, if you sort of do this in parts or pieces, if you will, and you get an answer, take that answer, do the next conversion, get an answer, do the next conversion, and get an answer. Remember, as we talked about in a previous lecture, you definitely do not want to do a lot of rounding. So you do want to kind of keep track of your significant figures, but, you know, take it to a few extra digits and just wait to the end to round it. Otherwise, again, if you sort of do it individually there, you'll be kind of moving yourself away from probably the correct answer. So this is dimensional analysis. This is how you're expected to show your work here in this class and pretty much all the other chemistry classes that you take. If you do not do that, you will not get full credit. So you do have to set it up and do that. What do you need to sort of show to get credit? Really, a lot of stuff sort of scribbled on this page, but really it is sort of this setup here where it can clearly see the conversion factors used, the units, and the answer with the right number of significant figures. If it helps you to write what was given, figure out the conversions and the equalities, you could do that. You don't necessarily have to show it, but you definitely do have to show, you know, for credit, this bottom part here and all the work that's associated with it. All right, so that is conversions. A couple of things we sort of touched upon, percentages. Obviously, if you're calculating the percentage of something, you take whatever you're looking at and divide it by the total amount and times it by 100. That should probably be fairly straightforward, I think. So here in an experiment, if we have 25 red flowers, 33 yellow flowers, and 22 white flowers, what is the percentage of red flowers? So really here we would get the total amount of all of our flowers. We would add them all together, which is what we see here at 75. And in this case, the percentage of red would be our 25, which is how many red we have, over the total, times it by 100 gets us to 33% of the flowers are red. We obviously could do that for the other ones. For yellow, we could take 33 divided by 75 times 100. And for white flowers, it would be 22 divided by 75 times 100. Another percent type unit I think I actually touched upon earlier is mass percent. We take the mass of what we're interested in divided by the total mass and times it by 100. The units cancel out here, and we do end up with just a percentage. So if we look at an example of this, a sample of nickel oxide is made up of 14 grams of nickel, 7.64 grams of oxygen. What is the percentage of nickel and oxygen in this case? So again, here we would add up the total amount, and that would be, in this case, 14 plus 7.64. That's going to give us 21.64 grams. By the way, we're adding here, so 2 decimal places is what we're looking at. So far, to find the percentage of nickel, we take the grams of nickel, which in this case is 14, times 100%. And if we take 14 divided by our total times 100, and we're looking at about 65%. It looks like they rounded a little bit there, so that's 65% nickel. By the way, since this is 100% of everything, we could at this point take 100% and subtract it. And if we did that, that would give us about 35% oxygen, since that's the only other element. Or we could do the same calculation, 7.64 grams of oxygen divided by 21.64 grams of the total times 100%. And again, that should give us our same answer we just got there, which in this case is 35% basically. So that looks like it is C, I think. If I picked the right one, it should be our correct answer. All right, the next thing we're going to talk about here is density. And density can be defined as the amount of matter that's present in a given volume. Density has several units, grams per milliliter, or grams per cubic centimeter. And remember, as we talked about, 1 milliliter is the same as a cubic centimeter. This is typically the units that you see for solids and liquids. Actually, gases will actually have a slightly different units. Grams per liter is typically the units that we see. I would say, though, for most of the time for us, these are going to be our 2 common units of density. Density of an object basically determines whether or not something will sink or float in it. Typically speaking, density of liquid water, if you ever need to use that number, is 1 gram per milliliter. Density does change with temperature, but in book problems and in most cases, if you kind of like need the density of water, liquid water, usually 1 gram per milliliter is usually what you want to use. If an object is more dense than liquid water, it will actually sink. If it's less dense than liquid water, it will actually float. The formula to calculate density is mass over volume. And as I mentioned a second ago, these are the common units that we do see for density. Density is like a formula, and we do solve for all 3 of those factors. So density is mass over volume. If you want the volume, that is mass divided by density. And if you want the mass, that is volume times density. Sometimes people remember this by the world famous, not sure how world famous it is, DMV triangle. Triangle-ish. Density is mass divided by volume. Volume is mass divided by density. Mass is volume times density. So a DMV triangle there sometimes will be a good way to remember how to rearrange that correctly. So let's take a look at an example here. A block has a volume of 25.3 cubic centimeters. Its mass is 21.7 grams. Calculate the density of the block. So again, here, take a moment, grab your paper, your pencil, your calculator, and see what you come up with. Okay, so in this case, we are dealing with density, so we'll use our density equation, mass divided by volume. Remember, a cubic centimeter is a volume. So we do have a volume given to us. The mass is also given to us, which is 21.7 grams. So if we just kind of check off what we have, we pretty much have everything we need. So the density here will be 21.7 grams divided by 25.3 cubic centimeters. So we'll take our calculator and divide it out. 21.7 divided by 25.3 going to give us a value here of 0.8577. I'll write the whole thing there, 0.751. The units do not cancel, so it's grams per cubic centimeters. But as you probably are thinking to yourself, seems like a lot of numbers there. That's probably not the right answer, and you would be right. So we do want to look at our significant figures here since we are dividing. This number has 3 significant figures. That number right there has got 3 significant figures. That tells me my answer should have 3 significant figures. That's a 7 next to the first 7, which means 0.858 grams per cubic centimeter should be our correct answer there. So again, you do want to watch out for our units and our significant figures and make sure that we do give everybody to the right answer, our number of significant figures. Let's talk a little bit about how we can get volumes. So we've talked about a couple different ways that you can kind of get volumes here. And one way is very simply, you can just basically take a volume reading. So if you take something in a graduated cylinder and it's filled up there, you simply look at it and you take a volume reading. Another way, especially with a solid, as we talked about, you can take the length times the width times the height, and that would equal your volume. And again, if they are all, for example, in centimeters, that's going to get you your cubic centimeters, which once again is a volume. Now, another very common way to get the volume of an object is volume by displacement. So the idea of volume by displacement, for example, if we filled a graduated cylinder up with a certain amount of water and we take a solid object and we drop it in, what is going to happen to the volume of the liquid? So take a second to think about it, and hopefully your answer is the volume will go up to like a final volume. Now, the solid object will actually displace a volume that's equal to its own volume. So if we actually take the difference in the volume of where it started to where it ended, that will give us our volume of our object, which is our final volume minus our initial volume here. So that's what we see here. Before she jumps into the tank, we have an initial volume there. She goes for a dive. She displaces the water. We now have a final volume. So again, if we take the difference in this container, and I can draw straight lines, we will have the volume of her. And in this particular case, I hope this is not just markings, but maybe a ladder to get out of that box, or I hope she could hold her breath for a while there. But volume by displacement is really a very common sort of way that we calculate the volume of a solid object. It's very easy to do. Just need some water or something like a graduated cylinder, and you can figure out how much volume is there. All right, so once you take a look at this one and give it a go, a student fills a graduated cylinder to 25 milliliters of liquid, then puts a solid in it, and the volume goes to 33.9. The mass of the solid is 63.5. What is the density of that particular liquid? So give it a go and see what you come up with here. Okay, so let's take a look and see how you're doing. So we got a couple of things given to us. We definitely have an initial volume of our graduated cylinder, which was 25 milliliters. So basically we got 5 milliliters. We then take a solid and our final volume ends up being 33.9 milliliters. So we're going to toss in there solid, going to rise to 33.9 milliliters. And we also have the mass of the object, 63.5 grams. So if we think about density here, which is our mass over volume, we have the mass. We do need to find the volume. So this is, again, a displacement situation. So we want the difference there. The volume of our object going to be our final volume minus our initial volume. And our final volume here of 33.9 minus our initial of 25.0 going to get us, when we do that, 33.9 minus 25, going to give us 8.9 milliliters. That is now going to be our volume. Now we have everything we need to calculate our density. Density is our mass divided by volume. So our mass is 63.5 grams divided by 8.9 milliliters. That will get us 63.5 divided by 8.9. That is going to give us 7.1 grams per milliliter as our density. Now, if you're thinking about significant figures, it is 2 significant figures because last part we did 3 significant figures divided by 2 significant figures. And really it comes down to here. Here we did subtraction, which means we look at decimal places, which means we should go to 1 decimal place. But this guy has 2 significant figures. And that was important because the last thing we did in terms of our calculation is we divided. So we want to look at significant figures here. And that is how we end up with 7.1. So again, we want to kind of keep track of everything as we go through our calculations and again, clean it up there at the end. Here is a table of densities, and water's highest density at 4 degrees Celsius is 1 gram per milliliter. So again, that is typically what we use for water. Again, it does change with temperature. By the way, the density of liquid water is different than the density of ice. Water is an unusual substance. Actually, in its solid phase, it's less dense than in its liquid phase. So ice actually has a lower density than liquid water. That's why when we put ice cubes in our drink, they float right at the top. And that's because what happens when water comes together in the solid phase is creates a lot of open space between the different water molecules. So what that does is sort of bloats the water molecules in the ice form or the solid form. If you think about density, density is mass over volume. That means that solid ice here will actually have a greater volume because of all that open space between the water molecules. They can't get as close as they can in the liquid phase, and that it bloats them and gives them a larger volume, which means on the bottom there is going to be a bigger number. Up on top will be a smaller number. That gives us a lower density. So water is a very unusual substance like that. Most substances are more dense in the solid phase than in the liquid phase. Let's take a look at some more common densities here. So obviously cement is more dense than water, so it would sink. The gas is less dense than water, so it actually floats on top of it. Let's take a look at one more example here. Whoops. A student needs to use 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt would they need to buy? A reminder that 1 pound is 453.6 grams. So I want you to take a moment and figure that out and see what you come up with. Okay, so let's take a look. Remember that cubic centimeters is a volume. So we have 150 cubic centimeters, which is a volume. We have the density given to us as 2.16 grams per cubic centimeter. Once again, this density we could actually use as a conversion factor. So we could flip it around and use cubic centimeters up on top, 2.16 grams on the bottom. So we're definitely using density as mass divided by volume. We have the density given to us. We have the volume given to us. So if you weren't sure what to do, mass would be good. And mass is in grams, which means we could then go from grams to pounds and sort of figure out what we need. So we would rearrange this, and the mass would be the volume times the density. I'm going to set this up actually more like a dimensional analysis problem. So I'm going to take my volume, which is 150 cubic centimeters. Eraser here. I'm going to go opposites here. So I want cubic centimeters on the bottom, which is this way. So we're going to go 2.16 grams per cubic centimeter. Cubic centimeters will cancel. And that's going to get us 150 times 2.16, about 324 grams of salt would be needed. If we're looking at significant figures, that is 2 significant figures for the first number. That is 3 significant figures, which means technically speaking, we probably should end up with something like 320 grams of salt is needed. Remember, though, that we do want to answer the question, which is we basically only need 1 box. We'll have some left over, as 1 pound box is 453 grams. We only need 320. So in this case, we would be good. So a couple of things, make sure you do answer the question that's being asked. And again, you can show your work here. So that is density. Let's talk a little bit about specific gravity. Specific gravity is the ratio between the density of a substance and the density of water. So as we talked about, density of liquid water is 1 gram per milliliter. Specific gravity is one of those few sort of units or unitless values in chemistry. A hydrometer is an instrument that's used to measure the specific gravity of things like battery fluid or urine to check on, for example, if the battery is still good. You could sort of figure it out based on its specific gravity. So if we look at something like this, the specific gravity, again, is that ratio of the density to the density of liquid water, which is our 1 gram per milliliter. Basically, the units of density cancel out. So, for example, proper kidney function, we do need to make sure it has a specific gravity. What is the specific gravity of urine? With a density of 1.031 grams per milliliter. So we would take the density of our urine, we would divide it by 1 gram per milliliter. It will give us a specific gravity here of 1.031. So that is how you calculate specific gravity. It essentially is kind of like the density value divided by 1. So it will usually end up being obviously the same. It just won't have the units associated with it. But it is used, like I said here, to see about proper kidney function and also to figure out like your battery in your car, if it's still good. One last thing I did want to talk about before we sort of finish out all of this, and that is a little bit going back to conversion. So, for example, if we had something like 32 cubic feet, how many cubic inches would that be? So if we were doing some type of conversion like this, we basically could use our inches to feet conversion. And there are 12 inches is 1 foot. And if we were going to do this, we could still use our same conversion factors, or 2 inches, 12 inches over 1 foot, or 1 foot over 12 inches. So if we were to start with our 32 feet cubed, we would want to go opposite. So we want feet on the bottom. So we would use this conversion right here. That would give us 12 inches is 1 foot. If I do it just like this, the feet and actually only one of the feet would cancel. So that's not going to work well. I actually would need to do it twice here. 12 inches is 1 foot. That foot would get rid of the second foot, which means I really need to do it not once, not twice in this case, but I actually have to do this conversion 3 times. And now finally, we will get rid of all of it. Now, when we multiply, that's going to be inches times inches times inches, which means we will end up with 32 times 12 times 12 and times 12. That's going to give us 55296 cubic inches in this case. Significant figure wise, exact number, exact number, exact number. 2 significant figures should end up here. So something like 55,000 cubic inches. Or again, you could do scientific notation. 1, 2, 3, 4. 5.5 times 10 to the 4th cubic inches here. Now you may be saying to yourself, could I just set it up like this? And the answer is yes, you could. But in my experience, what people will do is they'll actually cube the units, but not the number. So sometimes, and maybe it's better to just kind of spread it out and do them individually, so that you don't forget to actually do the number. A very common mistake, again, sometimes people will kind of just do it like that on the bottom and actually not do the number. So I just want to touch upon that type of conversion as well, just to make sure we kind of covered it. And with that, I believe we've come to, I can't believe it, the end of chapter 2. So thank you for watching. We'll see you on the next one. Have a good day and bye. Hello there. I hope you're enjoying this lecture or enjoyed this lecture. It is time, I think, for another chemistry joke moment. Let me see here. Well, we got one in the pocket. Let's see here. Yes. Why can you not trust an atom? They make everything up.